My name is Artem Eroschenko, and I'm the member of IT students team who took part in a project activity that was organized by our Department of General Physics in Novosibirsk State Technical University. And Alexander Baranov is our supervisor. I'll tell you about our work. Uh, it's modeling and software development at the virtual lab Tonomura's single electron double slit experiment. The developed software product will be just a simulator used for educational purposes in study of quantum mechanics by the first year students. And our work was completed this year spring when we were at our second year studying physics at university. So let's dive in. The quest for quantum basic understanding is essential for further progress in radical new technologies, and many young graduates for technical universities will soon be working in these new fields. The study of quantum physics becomes essential for them, but as analysis show, students face great difficulties when studying quantum mechanics. Studying quantum mechanics in general is quite challenging. For technical university, for example, one of the significant problems may be the lack of sufficient instruments to implement such experiments in reality. With the development of information and communication technologies, on the other hand, in field of teaching physics, a completely new tool has appeared, virtual physics laboratories. Virtual experiments delivered with computer technology, and they add value to physical experiments by allowing students to explore unobservable phenomena and link observable with unobservable. So, according to a poll of physics world readers in 2002, the most beautiful experiment in physics is the interference of a single electron in Young double slit. The experiment demonstrates the amazing property of reality, the corpuscular wave duality of matter particles. Randomly falling on the screen, individual electrons form a typical interference pattern. And the progress in micro and nanotechnologies has made it possible to carry out such experiments in reality. So Dr. Akira Tonomura's experiment was chosen as a real prototype for software implementation in our lab. A few words about the experiment itself. Akira Tonomura and his colleagues used the transmission electron microscope to implement the analog of double slit here. The biprism plays the same role for a wave function of a moving electron as a double slit. After the obstacle, the electron wave function just splits in two. But the two mechanisms of such transformation are quite different for double slit and the biprism. So we will describe the biprism here, which consists of a positively charged wire placed between two grounded plates, and it performs the electron wave transformation into two coherent ones. So the electric field distribution is not uniform between the charged wire and the plates. The two opposite horizontal electric field components cause the two electric wave functions after the biprism. And the two-wave superposition leads to a characteristic interference distribution for the electric wave function, and the square of it determines the probability of a single electron hitting the exact area on a scintillation screen of a microscope. The developed software product will be just a simulator, which will be used for educational purposes to study physics by the first year students. Therefore, the mathematical models used here must be simple enough and correctly reflect only the basics of this process. So the model will not take in account more complex quantum effects, such as decoherence, for example. So from all of it, the three processes were taken into account. The electron movement in electric field of a microscope accelerating system, the electron movement in a prism electric field, and the electron probabilistic occurrence on a scintillation screen, after all. The quantum mechanical concept of particles corpuscular wave duality is adopted for our mathematical models from the relativistic relations and electron kinetic energy increase association with accelerating voltage, we can obtain the formula for momentum of the accelerated electron. With this formula, we will compute the momentum after the electron has passed our acceleration system and the prism. The value from this we can also use to determine the electron de Broglie wavelengths when switching to the wave representation. And this representation we will use to describe the interference pattern to determine the probability of the electron hitting the region of our scintillation screen. Since the electron moves in a static field, the probability density is determined by the square of only the coordinate part of a wave function. And since the electron B prism in Tonomura's experiment is analog to Fresnel B prism, we will use the cylindrical wave representation to our wave functions. Taking all of this into account, our model uses the following expression to build the wave function and compute the probability density on the scintillation screen. Due to the use of cylindrical wave representation, the distribution interference nature is related only by the x-coordinate. And to simulate the interference pattern appearance in time, we will use the rejection sampling algorithm. Let's look to the step-by-step execution. Firstly, we introduce the function which represents the squared wave function. We then calculate the threshold, the C coefficient, which is just the maximum of this function. On the next step, we generate coordinate. We select some random uniformly distributed x coordinate. And on the next step, we generate a random value between 0 and c and validate the condition. If the condition is met, we just draw a point at the x-coordinate with uniformly distributed y1. If it doesn't, we just discard and generate a new x-coordinate, and the algorithm goes a new round. So we repeat this until the target electron count is reached. About the implementation, we here use the unity game engine based on the principle of clean architecture. This approach ensures low coupling, high testability, and strict separation of concepts between the logical layers. This system consists of several layers. The first one is a domain layer, which contains contracts and models without any external dependencies. The application layer defines application-specific use cases that coordinate models and interfaces from domain layer while being completely independent from the UI and visualization. Infrastructure layer contains concrete implementations of interfaces from previous layers, including the physical core, for example, and presentation layer, just the outer layer for user interactions and Unity UI models. About the integration strategy, the simulation core is encapsulated in the static class, independent from the architectural layer of application. So integration is performed using the adapter pattern. This design preserves the independence of the mathematical core, as I said earlier. For our visualization, 3 models from the site Unity Asset Store were used, and we just modeled all of this with Blender. And for demonstrating it, I want to switch to our app. I suppose you can see it. So in the background here, after we executed the main file, we can see the microscope, and here the 2 virtual monitors. Camera by default is using the just look around mode. If we want to just try to use the microscope, we need to go into the focus mode by clicking on the monitor. The monitor by default are turned off. To turn them on, we need to click the button on the bottom right corner. The right monitor is used to set the values, the initial values. We can use a slider for it or just a text input field. We also can set the number of electrons here and the speed of the experiment itself. And the left monitor is used to show the result here. And I just tap this button, and the interference pattern has appeared. Also, the adjustable grid were provided to make measurements for our virtual laboratory. And here are how we can implement such things. So the presentation here. And so as a result, having completed the necessary stages of software development, we created a real product, the virtual laboratory Tonomura's single electron double slit experiment. The program interactive capabilities allow for a large number of virtual experiments to study an amazing property of reality, the corpuscular wave duality of matter, and etc. Testing showed that the virtual laboratory can be used in educational purposes to study quantum physics by the first grade students. So thanks for your attention. I'm ready to answer your questions.
That's interesting. And how long did it take for you to develop this software?
It's was about approximately maybe a month, or yeah, quite a month, or with a half of it.
And how many people were
3
developing?
people. Our team of 3 people. Here we are.
Okay. Is it open source?
Yep. Now it's in our GitHub, so you can download it and just execute on Windows, because the build is only for Windows there. But also the Unity engine is we can build it for other any systems because of the Unity engine.
And why did you decide to use this Unity engine?
Because it's quite simple nowadays, and we wanted to use the OP style programming languages, but the Unreal Engine, we thought that the Unreal Engine is quite hard for this project, and just why not to use Unity, which model instrument is quite simple, and we don't need any other studying to build such virtual lab.
Did you use unit testing?
Of course, because every one of us built his part of a program, so we need to test it this way.
Okay, because this interactive reality looks like an extra feature which is not really required to understand the visual effect of this experiment. You can just do it, probably just render it on the web screen, for example, on the web page, using JavaScript or something like that. So
yes, but
you decided to choose this technology. That's why I
yes, because of an optimization. Because we need to make sure that this lab will start on our just old pieces that are located at our university. So we needed a quite good performance.
Okay. And is it going to somehow contribute to future students who will come to the same subject in the future, this experience of yours, or maybe the application that you created? What's the plan to transfer it to others?
We just...
or the project is closed, and that's it?
No, it's not closed. We will implement something that I call the level up of this project, and because this project doesn't take into account the coherence, for example, we will add them in a future project. It just will be the level up for students. So they just completed this virtual lab, and maybe after some months of studying quantum mechanics, they will complete the another level of this app. So this how they will increase their studying.
And they will work on the same software, or they will create new versions or different versions.
They can create some different versions or the same version of this app, but updated one. Because of the clean architecture principle that we applied here, the parts are adjustable and scalable, and there is no need to maybe rewrite the existed code here. So why not?
Okay, sounds good. Okay, then thank you very much. I think we have some time left for the next speaker, but thanks for you. Can finish here. Okay.